difference? Yeah, this is better. Okay. Great. Well, thank you very much. Yeah, it's a wonderful opportunity to be back at ITAMP. It's always, a lot of wonderful memories, and thanks, Hossein, for both organizing this meeting and also creating this, amazing, family of generations of ITAMP fellows. So a bit inspired by Anna, I wanted to start. Well, no, actually, wrong. So I, maybe before going into the overview, so I put the slide in the wrong place. Just kind of a very brief overview. I was at ITAM in 2014 to 2018. And I remember starting my ITAM journey by actually meeting Misha Remeshko and getting drunk with him. That was still before I had my PhD. He was just coming to Vienna and I was just going to leave. So that alleviated a lot of anxiety, but excitement as well. So thanks, Misha. And then, being here, I really was very fortunate to spend time together with Richard, Svati, and Stefan, where we came around the same time. There's many, many fellows that I met over the time. Like I said, there's really a wonderful kind of community that Hossein kept together and looked out for, like Nicole mentioned. And I really appreciated it. It was really a lot of intellectual growth and also personally a wonderful time. And then, of course, many, many still collaborators. And, I just to highlight, for example, Rivka and Hannes, where we discussed a lot of physics. Johannes Beauregard from Misha's group, who's also now here, and we still work together, and Shimon Kolkovitz, and many, many more, Biho and Nicole, and so forth. So, it's been great, but also in terms of mentorship here from Misha, I met Jun Yi here, Avi Loeb as well on the astrophysics side. So it's a very unique place, which I'm very grateful for. Okay, now let me go back with all the slides to the overview of my talk. What I want to talk about is the gravity-quantum interface, which is a little bit maybe similar to Nicole's story, that is somewhat of a niche subfield that has been growing over the last decade. And I've been very fortunate that kind of growing with it in the same way, and ITAMP also giving me the opportunity to explore that independently for quite a while. And so here I want to talk about a recent result, which actually goes back to some of the ideas thinking about here at ITAMP, namely on the detection of single gravitons. Okay, and so I want to guide you through it, how we solved that problem. So first I'll talk a little bit about what does it take and why is it difficult to detect single gravitons, and then how do you overcome these challenges in new ways that leverage a lot of recent developments. And I'll talk a little bit about the experimental feasibility of actually doing that. Okay, so now let me go through a talk. Just before I start, just kind of a very brief overview of, in general, our group and the field. It's really at the interface of AMO physics, AMO theory, and its application for fundamental physics, with a particular focus of fundamental physics being gravity. So different aspects of general relativity, tests of general relativity, as well as new physics and quantum gravity. And so this stems from just, controlling novel quantum systems in new regimes, and here highlighting, for example, a research that Rivka has been driving forward very much, where you kind of have new capabilities with systems. Quantum sensing in general, how do you use new systems and maybe new sensing paradigms in order to create quantum advantages, and then applying it to certain questions for high precision measurements, such as gravitational wave detection. And so here are two works. One was with Swati and Keith Schwab on detecting gravitational waves with modern quantum mechanical bar resonators, and another is with using optical atomic clocks, which we explore together with Misha and June and Ron. And then there's other theory questions one can ask, namely applying AMO techniques towards questions in cosmology, and what type of maybe novel, interesting phenomena might arise that you simply overlook when you just have the standard high energy field theory approach. And then most interesting to me is this right part here, is where you really apply these ideas towards test of quantum gravity. Novel questions that we can ask about exploring new parameter regimes and constraining experimentally maybe some questions that relate to the quantization of gravity or lack thereof. And it's related to that are also just in general GR effects, how they affect quantum systems, Gedanken experiments, discussions whether, what kind of conceptual questions you can ask. And then here finally, this kind of new approach that we now showed that is also feasible, namely also looking at quantization of gravity from gravitational waves. And that's single graviton signatures. So in this talk, I want to focus on this, but I want to mention two of my postdocs also came, and they will talk a little bit about some of these other aspects in a poster session if you're interested. Okay, so now there's of course a core question: can gravitons even be in principle detected? I think the standard answer always, we all know that that is not the case, and there's very good reasons for that. Okay, and so one reason is that it was hard enough to detect even classical gravitational waves. So LIGO detects gravitational waves when they're really from this extremely violent bursts and mergers of black holes, where it's tremendous amount of energy, and you can barely detect that. Okay, and so you really would need something like 36 orders of magnitude improvement of LIGO in order to be able to resolve a single graviton. Similarly, you can just compute the cross-section on the particle level. It's kind of on the Planck area scale. And so you might think about colliders, it's not feasible. So all of that is unfeasible, and so people have, of course, asked these questions over decades, just in general, even as a theorist, but the answer is always no. There's no way, and people speculate that maybe you can never do that. Now, what I want to show here is our recent result, where we show, that this can actually be done. And this can actually be done for many reasons, which I'll outline, which go around these problems. And that was in many ways inspired, starting thinking about here being at ITAMP, when we worked, for example, on quantum mechanical resonators that can detect gravitational waves, as well as the optical clocks. And so there was this question lingering, like what would it take actually to push it into the domain where you can see some type of signatures of gravitons. And that kind of stayed with me for some time, and now we have, I think the resolution to that, how this can be done. Okay, so before going to a graviton, let me go to the photon. Now, of course, it's preaching to the choir, except you have to forget a lot of things that we already know. So I want to go back to the photon in the very early days. Namely, there's also, in fact, a little bit of a controversy what we today mean of the photon that we kind of use in a general sense. I mean, here, Willis Lamb, for example, didn't like that term. And so really, we don't want to talk so much about this kind of hand-wavy things like wave-particle duality or really a particle, but rather very specific things. So this picture, of course, was wrong, I showed, but specific things, namely, in the early sense of a photon, was the question of if the electromagnetic field is quantized in discrete amounts of energy. Okay, and so that kind of is what I mean here by a quantum of the field. And of course, you can go beyond and talk about whether there's like truly non-quantum nature of the field by looking at quantum mechanical statistics. But here I'll focus on this kind of discretization of the energies that you can observe. Okay, so now how would you look at how gravitons actually interact with matter? This is something that we can compute. There is nothing, you don't need any new theory for that. This follows from normal gravity and quantization of it in the linearized regime. So for example, if you open Weinberg's book, there is a beautiful calculation on that where he actually asked the same question. Hey, what would it take to measure a single graviton? And so what he computes, it's a scattering cross-section, namely where an atom is excited from one level into a higher level, except it's a quadrupole transition. Okay, and you can compute it directly and you get an answer. And the answer he gets is an atomic transition from through D to 1s, so like a D excitation and a graviton is emitted, and he finds that the rate of that is 1 × 10⁻⁴. 44. It's not fully correct, even though everything is correct. He seems to have plugged the numbers in wrong. So there's a more recent paper by Bonn and Rothman that went through it very carefully, and they get the same answer but different numbers. Anyway, so it's a little bit better, but it's still hopeless. Okay, now, of course, he concludes there saying that, look, it's just, in principle, there's no chance of ever observing such a transition. And so this is the type of question that we are revisiting. Can you observe such a transition? And, the upshot is yes, you can, and I'll show what modifications you need. Okay, so now, just very quickly, I hope I have enough time, but just to say, like, how would you proceed even with such a calculation? Since we're all theorists, we do know the interaction Hamiltonian in the linearized regime, and that's all we need. Okay, and it interacts between matter and the kind of first-order perturbation of the gravitational field. And then for matter, we can plug in something like an electron, for example, and then that's what he does, Weinberg. And then for the gravitational wave, well, you plug in the gravitational wave as we know it. You can write it down in Fourier components, and then you can quantize it in principle. Of course, who knows empirically if that's correct or not, but there's no problem theoretically to do that. Okay, and so that's how the calculation proceeds. And then once you have this interaction Hamiltonian, you can look at something like a rate, something like a Fermi golden rule or something like that. That's what they did in the old days. Okay, so you plug it in, you find some kind of transition rate, with a density of graviton states, and then you find this result just by plugging in, let's say, these quadrupole moments of the atomic system, for example. So this should just kind of to just give a conceptually of how such a calculation looks like. Okay, and this is how you get this low number. Okay, now what we looked at is modifications to that. Namely, none of the theory is wrong, but can you think about modifications of that where it could in principle be possible? And the answer is yes. The first one is you can think about, instead of atoms, you can think about macroscopic systems. Why is it interesting? In the gravity in particular, because it's the mass quadrupole moment that is the fundamental charge that's relevant. And I think it commutes with others, but that's a separate question. But the mass quadrupole charge is, of course, scaled up if you look at now macroscopic quantum systems, which nobody was, interested in, or it was not relevant back then when people looked at it. The second aspect is that we don't have to look at just spontaneous emission. In fact, Weinberg and others, Dyson, have also looked at stimulated absorption. Okay, so you can look at a different process where you have a stimulated event where it's still a single event, but it's stimulated. And this is interesting, in fact. And the last part is that we have quantum sensing capabilities that allow us to resolve discrete energy levels in principle and the dynamics between them. Okay, so all of these are, in fact, very recent developments. And the upshot is that when you meet all three of those, then it is actually possible in an experimentally realistic way to detect single graviton transitions induced by single gravitons. Okay, and now the rest of the talk is just going through it in a little bit more detail. Okay, so first let's go away from atoms. We want to talk about macroscopic quantum systems. We just want to have the correct Hamiltonian to apply it into this coupling. So the Hamiltonian is given by the coupling to the stress energy tensor, and here we can just do this kind of calculation where we build a collective system out of n atoms. And I don't want to go, this is just technical, you just kind of build n atoms and you find, of course, collective modes. And the point is that in the end of the day, you can change your modes, then you have new modes. Instead of thinking of n atoms individually, you have new collective modes that you can look at. And then what you get is you get an interaction Hamiltonian, which consists of two parts. One is a part, one is a part which is basically n Weinberg atoms, in the sense that each atom gets a little bit squeezed, okay, and then it has a certain tiny probability to be excited into a quadrupole moment. But there's also a collective part, which is an overall kind of collective behavior of all the systems together, which scales both with mass and the length of the overall collective system. So you have like a scaling effect so it's not just simply n times the atom that you get in the result of your collective behavior. And so this in fact dominates, and so your interaction Hamiltonian of a massive system scales then with, in the end, square root mass and the length of the overall system if you have like a 1D chain. Okay, and then we can look at this Hamiltonian instead, just doing the same. Now let's look at what's the transition rate there, and you can plug it in and so forth, and what you get is, well, it depends on just a few parameters of the system, such as speed of sound velocities, like stiffness of the system, the mass density, and so forth. And then when you plug in typical numbers, so this is in effect just a cylinder, a bar detector in some sense, just built up from the ground up quantum mechanically. If you plug in numbers, some reasonable numbers, what you get is the spontaneous emission rate, which is 7-8 orders of magnitude better than Weinberg. So much, much better, but of course still far away from something that's detectable. Okay, so that's one aspect. Now you can add the second aspect, namely you don't need to look at just simply spontaneous emission. You can look instead at stimulated emission. Why can you look at stimulated emission? We can't create gravitational waves, obviously, but now today we know when they're coming. And that's completely different from back then. So they've been detected, so we can always actually know and post-select on events where gravitational wave has been present. Okay, and if you make this calculation for stimulated emission and so forth, I just show in the result. Again, you have, like, for example, aluminum bar. Here, just a throwback to Joe Weber, who really pioneered the field. This was his aluminum bar. If you plug in numbers like that, what you find is that if you now take a known gravitational wave, the first detected gravitational wave with its amplitude that we know, what you find is that, on average, if you could resolve it, you have a single graviton exchange per second. So you're in an extremely sweet spot. Namely, you actually have graviton exchange processes on the quantum mechanical level, but you don't have many of them. You have very few. So what you win at is two things. Actually, the only reason why gravitons are relevant is precisely because you barely interact with them. So the intuition is the exact opposite. It's not because you barely interact, you can never detect them. It's the opposite. Namely, you have this extremely violent event, and yet, on average, there are certain scales where you only extract a single graviton from it. Okay? And the question is if you can kind of resolve that. Okay, and so in many ways this is analogous to the early days of quantum mechanics where people looked at the photoelectric effect, because this is also just stimulated emission of radiation. And of course, you know, that was the postulate of Einstein, that this, you know, that it's an exchange of single quanta, that this must also correspond to the quantization of the actual field. And that, of course, for a long time was not accepted, and other experiments were needed and thinking in order to really get to the full quantum picture. But in many ways, it's the same process. You have some kind of classical, strong external field, and that excites a single quantum transition. And then this single quantum transition corresponds to exactly the energy exchange on resonance between both of these, the field and the matter. Okay, and that was used, for example, here by Millikan to then slope it out and then measure h bar, for example. What's interesting is in this paper, Millikan still says, yeah, the formula is right, but Einstein, of course, is wrong. Like, you know, there's no way that the field is quantized. Okay, and that's the same caveat here. So, so there will be, and I'll discuss that a little bit in the end. Okay, so the analogy here, just to kind of put it in a different perspective, it's really kind of what we want to see is the stimulated absorption or emission, but the key point is that it's the discretization of energy. And so how do we know really that this proceeds in discrete amounts? So that's the key. The ray doesn't tell us that. Okay? And so what we want to do is we want to really show that you can zoom in on the individual events so that they can really have you know, certain well-defined energy levels of your matter sector. And then as soon as you herald to some kind of gravitational wave event, you can really see that there is a single click, that you really change the amount of energy by one quanta, which means that you cannot look at these Fermi golden rules or averages or anything like that, because any number is possible. But you really want to post-select on single quantum events. In other words, you want to monitor quantum jumps in your system, because that is an indicator of the discretization of the energy exchange. Okay? And so you really want to look at these kind of induced quantum jumps by external gravitational field. And my student, he called it then the gravitophononic effect in some sense, just an analogy. Okay, and so how do you do that? And so now there's many problems with this kind of, how do you post-select on a single quantum jump? Sorry, is there anybody telling me the time? Oh, I see, over there, the clock, that makes sense. Right. Okay, so now with gravitational waves, with the real ones that we observe, there is one issue, I mean not issue, is that they're of course not continuous or anything, they actually last a very short time, they change frequency. So here, I don't know if one can hear it. Oh yeah. So that, for example, was converted into sound, the frequencies of a neutron star merger. Okay, that's nice because it lasts so long, otherwise it would just be a blip. So what you hear is the frequency is changing and it's changing in time and so forth. So what we really wanted to do is that, okay, this was just kind of an introduction of how do you roughly gauge of what you need to do, but we can solve this Hamiltonian dynamics exactly, because it's a bilinear Hamiltonian, now just with gravity instead of the electromagnetic field, but you can solve this exactly for any arbitrarily waveform, in fact. And that's what we want to do. And so you do that you know, with standard techniques. Oh, that's it. Okay. Right. So yeah, so you can do it with standard techniques, and of course. Okay. All right. I'll stay here then, or maybe I can if I unplug it. Yeah, people keep telling me to move away from Windows, but okay, maybe I should. Okay. Oh wow, no, I think my whole computer is, sorry. So you can do it, and not to waste time. I mean, okay, you get like an exact unitary what it is, and it will be a displacement operator. It depends on the strength of the gravitational wave and its time profile. And so you have this integration here, basically building up resonance over time, but it's like a transition through resonance of the system. And then, it's just an exact solution. And now with this exact solution, we can tell what's actually happening to the matter. Namely, as the gravitational wave passes, it will be created in some specific coherent state where beta depends really on this gravitational wave profile, which is captured by chi. Wait, I have a, sorry, I got a little bit distracted now from my computer. So it depends on the gravitational wave profile, and you can use any arbitrary one now. And those we know already from the LIGO detections, how they look like. Okay, and then what we want to do is we want to post-select on only a single transition. And so the probability of a single transition is, of course, given here by this number for a coherent state. And what we want to do is maximize it. So we want to find a parameter regime where it's maximized only a single transition, namely which we can post-select. And the single transition is then, the probability of that is about 37%. Okay? And then, so what it looks like is you would prepare something like a resonator at the right frequency in a ground state, and then as there is like some kind of gravitational wave passing, there is a certain probability that it will be excited only to the first excited state. Okay, and then this probability you can optimize because it depends on the gravitational wave form and the system parameters. And so depending on which form you choose, there's different system parameters that would be optimal for it. Okay, and so you can optimize, for example, the mass of the system. Okay, and then you can plug in here chi from, numerically from LIGO known forms, or we have also an analytic approximation. Okay, I'll just skip through it. So this is just kind of, you would then assume something about like how exactly does the gravitational wave interact with your system, and we know how that looks like depending on the source. Okay, so it could be black hole mergers, neutron star mergers, or some speculative sources. Okay, and then what we did is we looked at different sources, and we looked at the type of parameters you would need in different cases. In many cases, it's kind of irrelevant. The probability of a single graviton detection is just kind of very far away from being realistic, but there are certain cases where it's extremely realistic. And the best case, for example, is the neutron star merger that has been observed by LIGO in 2017, and it has the right amplitude, the right frequency, and especially it lasts very long. And so there what you can find is that with a mass of around 20 kilograms of a system, and you have to combat noise, so something like millikelvin cooling of the external thing, the whole system is in a ground state, Q factor of 10 to the 10 or something like that, then in principle you can have the probability of a single graviton excitation within the window of the gravitational wave passing. So there's like if you detect for like 10 seconds or something like that, there will be a sizable probability to having a single graviton event. So this is very hopeful, meaning that you could have resonators that exchange energy. So you can never do it with LIGO, because here the idea is that you have to exchange a single quanta resonantly between each other. If you see then a single excitation, such as in the system, then you can deduce that this was because of single graviton exchange. Okay, and yeah, so this is, in some sense, you need to improve bar detector technology, which has all been shut down. And then you have to supplement it with ground state cooling and then quantum sensing of quantum jumps. So it's a very difficult task. So I don't know, if you wanted to do it, it will take decades. But the point is, you can do it. The numbers are completely reasonable. There's nothing preventing it from it. Okay. Now, and the bar technology, in terms of Q and T factors, is about like maybe 2 orders of magnitude need improvement. So yeah, but this is the smaller challenge. The bigger challenge is really the quantum sensing of it. Okay, and so for the quantum sensing, I'll just briefly mention what you really need to do. You cannot measure position as they always do, as the LIGO does, and also bar detectors. You really want to do a Q and D measurement of energy in order to know that this is a discrete transition, because otherwise you can have any arbitrarily continuous value that you can have. But you really want to know it's only 0 or h bar omega, because what if it's 2 h bar omega? Could just as well be. It will be completely consistent with all of physics that we have, that it never exchanged, when the graviton energy is different. So you want to make sure that this is exactly the amount, and you need this kind of monitor of quantum jump through time continuous weak measurements that you can model. So if you have like some kind of interaction with couples to the energy of the system, okay, and here we just did a few runs, kind of like simulations of how such an experiment would look like. You anyway have only 37% success probability, even if you're ideal. And so you have to you have a duty cycle. You basically run the experiment for like 100 seconds, then you switch off, run again, and so forth. You never know when the gravitational wave comes. So that's one of the issues. So you have this time continuous energy monitoring. But here, for example, if you have like this pink region, then there really was a quantum jump induced, and you would catch it here from the weak measurement that would tell you that there's a probability of being in a ground state is now 0, and then the first excited state is 1. Okay, and so you really need to combine these ingredients. Also, what is key is that you want to correlate to LIGO detection, because now we talk about stimulated emission. So how do you know? You need to know that, not only that there was a gravitational wave, you need to correlate, post-select on that, but also what amplitude it is and frequency in order to show this Einstein relation of frequency matching. But that's how this experiment will look like. Okay, and then now I just want to briefly say that, like, what do we learn from such an experiment? And so this experiment, you can, of course, the gravitational wave is semi-classical. Only the exchange is quantized, okay? And so really what you're probing is, well, there was a big coherent state of the gravitational wave, and you extracted a single energy quanta from it. This is very different from just measuring that the input itself is a Fock state, okay? So this is not measurement of quantum statistics or some kind of negative Wigner function or some kind of state tomography. I don't know how to do that. Maybe there's a way. So it's not on that level. So it's not on the level of some kind of, this kind of modern quantum benchmarks. It's more on the level of an old kind of quantum mechanics, where the idea is the following. With additional assumptions, you can tell that there is an exchange of single quanta if energy is conserved between those two systems. So it's not a proof of the quantum nature of gravity, for which you really would need this kind of higher order experiments, but instead it's a demonstration that single quanta of energy are exchanged between two systems in exactly the ways we expect. And again, it could be completely different. Maybe it's not exchanged actually in exactly the same way. So there's still some input, but of course it's not a proof of quantum gravity. It's more like if we assume gravity is quantized, we can really zoom in on the level where single quanta are exchanged between matter and gravitational waves. Okay, and very similar photoelectric effect. It's not a test of quantum electrodynamics or anything like that, but it's a first step towards some indication and some demonstration of that there is, something quantized in the field, otherwise you get into trouble, such as violation of energy conservation. Okay, and then I think I'm over time. I apologize. I just want to say that the way I see it is a little bit of a different class of now novel experiments one can think about that try to probe the quantum and gravity interface. One class is trying to test maybe new models of interactions. Like, is there a gravitational collapse? Is there maybe a wrong commutation relation? Is there maybe some kind of like Jake pioneered in like measurement and back action, which is more classical between gravitational systems. Another class is like to test, really kind of create quantum states of matter and see how they gravitate. And then there's new effects that arise there. That's a class. And there the challenge is really to create quantum states of matter. And here what we look at is like you really look at quantization stemming from gravitational waves. You don't need quantum states, you just need the ground state. It's much easier. But the challenge is to do quantum sensing at these macroscopic levels, really distinguish energy levels there. And so it's a different type of class of possible kind of input into quantum gravity. Okay, and with that, just want to say that it is possible to gravitational waves, and it's not that people didn't think about it before, they thought about it, but in the way that was known back then, namely atoms, and there was no gravitational wave detection, no quantum sensing. Today, with all these new capabilities, we can show that there's a completely different answer to this 100-year-old question. And so we can design a photoelectric effect essentially for the gravitational waves, and having LIGO is essential to kind of herald on that. But you could also look at speculative sources. They look anyway at like gigahertz gravitational waves. There it would be so much easier to detect single gravitons, which just unfortunately they don't exist most likely. Okay, and then with that, I want to thank my team, students and postdoc working on that, of course. And I want to say both Josh and Constantine here have a poster on completely different topics. Yeah, thanks a lot for your attention.
I think we have time for one question then. Yeah, sorry, I always forget. And I saw Just Chris turn it on. No.
Thank you.
On? Oh, yeah, there we go. I think I'm just missing something. Isn't it really just a test, like your whole setup is assuming quantization of the phonons and doesn't really tell us that the gravitational, like, could it have, once you modeled the phonon system as being discretized, could you have had a different answer?
Yes, you could, exactly. So that's I think, precisely the point that one needs to go back and kind of forget a little bit things. So the way we think about it now is like, well, you know what, we have the semi-classical limit of QED and we can explain it. And that's right, you could. You don't need to quantize it, you really quantize the matter. Now, there are certain things that would go wrong if you just do that. So the semi-classical limit, for example, violates energy conservation. So if you assume that the quantization of matter induced a quantum jump, where did it come from? So if it's on resonance, you could deduce that, well, that was a single graviton, if you believe quantum physics. So this is one way to say that if you believe quantum physics, you know, this is the regime where you really see the exchange. And so, you know, you really, the quantization of matter will tell you about the other thing as well. There's another aspect to it, namely, you could have a completely different answer, because it's our bias that, yeah, of course, we just see quantization of matter. Well, like I said, what if gravitational waves are quantized in 2h bar omega? It would be completely consistent with all LIGO detection. You could build coherent states out of that. Now, you would never see a single transition or something else. And so there's absolutely no, there's a lot of room for possible surprises. There could be other things. You could look at, for example, is it equal, the stimulated emission and absorption probabilities, are they equal? So you can start exploring this regime even if you only quantize the matter. Of course, always with some additional assumptions. So that's why I'm saying it's a little bit, it's not a test of QED, but it's the early days where you start thinking like, hey, maybe I really need a photon. You can kind of start exploring this early question. But it will not be a proof of quantum gravity. So that's precisely the statement that you really here only look on the matter sector and try to deduce something about the other one. So you cannot use it as a proof that you have like a quantum state of gravity.
All right, real quick, in the back.
Yeah. So if you just focus on matter, so Penrose had this proposal that instead of quantizing gravity, you could gravitize quantum mechanics, right?
Yeah.
That you could add some term to Schrodinger's equation depending on mass, right? Could you say something about that potentially, or like deduce a test that would say, okay, this is wrong and this is right, like?
Yeah, it's an excellent question, exactly the right question. I don't know the answer, but that because they never gear towards these type of questions. They're always geared about, oh, what if my mass is big, what happens? And here it's a completely different regime that haven't been studied that much, and so I don't know how much you could constrain such of these models or other models with this, or how they would be inconsistent. So exactly, that's a very interesting question. I don't know.
Last question.
My question is my question is concerning the model of the solid which you are interacting with. What about nonlinearities of the phonon interactions? Are you considering optical phonons there or acoustic phonons?
Acoustic.
And I'm wondering if it's acoustic, why don't you get, I mean, you would have to cool every single mode because otherwise the non-linear phonon interaction terms become important, which are scaling, not so favorable actually.
You know, you're right. So first of all, it's acoustic modes, and then we look at, so it's internal acoustic modes. And you're right, we model them, you know, just by this kind of, sorry, where is it? I went too far. Why did I do that? Yes, exactly, right. So we indeed model them as having, you know, like each atom locally and then just being displaced harmonically near each other and then interacting with each other, nearest neighbors.
Actually, in sapphire crystals, you get these n-harmonic.
Yes, so you're exactly right, and there would be, of course, a difficulty with this. Okay, first of all, you could, in principle, think about the Q factor of the system, like how much does it do? I mean, let's say the easy way out is to say that we do really want to herald on a LIGO detection. And so we could monitor without it for a while, say it's like 40 seconds, then you would herald maybe with several, 2 detectors or something like that, I mean, in principle. So this is kind of a cheating out of this question, but I think it's reasonable that you would say, like, look, by itself, there could be so many things that go wrong. You literally just have energy excitation. There could be millions of reasons, cosmic showers. But you try to herald maybe on detection. However, of course, you want it to have it reasonably low such that your ground state really remains maybe for like 100 seconds. So that's why we assume this Q factor 10 to the 10, 1 millikelvin, that keeps you in the ground state for like sufficiently long time if you're not unlucky. And, yeah.
Thank you, Igor, one more time. So our final speaker of this session is Swati Singh. I should mention both Swati and Igor are both recent career award winners, and I was very privileged to be able to push the button on their award.
Did you push the right button? Thanks for pushing the right button.